Hi, so today we're going to look at interpreting molecular spectra and determining molecular structure as it relates to our mass spectrometry. A quick review of the parts of a molecular spectrum, where we have a molecular ion, and that would be the species that was formed from the removal of a single electron from a molecule. And that tends to be the ion or the part of the spectrum where we find the peak with the highest mass. So in most cases, you will look to the right of your molecular mass spectra, and that cluster, if there is more than one peak, is going to be an identifier of your molecular ion peak. And in some cases where it is present, you may also find an M+1, an M+2, or maybe even an M+4 peak. Now we look more specifically at the M+1 peak at our Cape level because that then is owing to the presence of a carbon-13 isotope, which has a relative abundance much smaller than the carbon-12, but it will still show up in certain molecular ion clusters because of its relative abundance. So we have our molecular ion and our M+1 peak, which will be at the highest mass furthest to the right of your spectrum. We also see that we have our base peak, which is the one that has the highest relative abundance, and that is usually formed by the most stable. Because we're always measuring a relative abundance, it is the one that will have the highest abundance, that on the scale will just relatively be 100, and everything else then will be relative to that. Your most stable fragment, of course, could be so much higher than your M+1 peak. So we will see in some examples where the M+1 peak does not exist at all. So we have in a general spectrum, this is what we're talking about, the molecular ion cluster, where we have an M peak, your M plus peak, and your molecular ion peak, and your M+1 peak. And that is, as I said, usually at the far right, and it is the most easily identifiable peak because it is really the total mass of your molecule. So if we were to look at a simplified mass spectrum of pentane, we see that in this particular example, if we add up the carbons, the hydrogens that make up pentane, we find that they add up to 72. And so the molecular ion will be present at 72. In this particular example, there is no M+1 peak because of its relative abundance being very low in comparison to the base peak. So in Unit 1, we looked at interpreting atomic spectra, and we would have seen something like this whereby we analyzed a sample of boron, for example, and we got a peak at 10 and a peak at 11. These peaks are strictly due to the fact that this element will separate into its distinct atoms, and so we saw that there was an atom that had a mass at 10 and an atom that had a mass at 11. Similarly, when we saw something like zirconium, because the element would have separated into its individual atoms, we saw that it had 5 peaks, each having a different mass. And this is an atomic mass spectrum, and everything in here is owing to simply the isotopic mass of each of the items, and their relative abundance will vary. Now, when we look at a molecule, chlorine for example, we see that there are 5 peaks on the chlorine mass spectrum. We're familiar with chlorine having an isotope 37 and a chlorine isotope 35. However, to the far right, we're seeing 3 additional peaks at a mass of 70, 72, and 74. I invite you to pause the video now and see if you can determine the identity of the peaks at 70, 72, and 74. What we have found, because chlorine exists as a molecule, the isotopes 35 and 37, not only will they be present as the individual atoms, but the molecule itself, having simply lost an electron, is going to be present with the two masses of the elements combined, of the atoms combined. So we see that there's a chlorine 35-35 molecule that will have a mass of 70. There's a chlorine 35, chlorine 37 molecule that will have a mass at 72, and there's a chlorine 37, chlorine 37 molecule that will have a mass at 74. These are the result of simply the chlorine molecule being ionized, whereby it would just have lost an electron. So we find in this case that there's a molecular ion cluster because each of the three types of molecules that are possible are going to be present on the mass spectra of the molecule. So this gives you an idea that when we have more than one atom that will remain combined or form a molecule, that the spectra becomes a little bit more complex than just the individual atoms. When we look at some molecular spectra, this is here to just simply show you that there are some atoms that will give you an M+2 peak, your sulfur, chlorine, and bromine, for example. Again, M+2 peaks are not common in our syllabus because they refer specifically to being able to identify the M+1. However, in the case of chlorine and bromine, if you're given a halogen or alkane, it is useful for you to be able to recognize if an M+2 peak is present, because then it gives you an idea of whether you have a halogen that may differ from its other isotope from a mass of 2. So when we look at some general fragmentation patterns, we see that alkanes, like other types of functional groups or types of atoms, have very specific ways that they will fragment. So your alkanes will fragment in such a way that we see a pattern arising where the fragments differ from each other by 14 atomic mass units, which is the result of that CH2 group. We also see that they tend to fragment in such a way that they create stable carbocations if it is possible. So if we look at the example here, which is your decene, we see that on the right-hand side, we have a molecular ion, 142, which is the mass of decene. If you look very closely, you'll see that it has an M+1 peak, but again, the M+1 is very, very small relative to the base peak because it is a fairly large base peak at 43. So you can perhaps come up with how many carbons and hydrogens would have had to combine or would be in the fragment that will create a mass of 43. Now, to the right of that, you see that there's a mass to charge ratio of 57. That then goes to 71 and 81, 99, 113. Each of these differ from each other, and these are major peaks in the spectrum, and they differ from each other by a mass of 14 because every fragment differs from each other through the loss of a CH2 on the chain. So you can imagine that you just keep losing a CH2, losing a CH2. And one of the things that one has to appreciate when looking at a mass spectrum is that every single peak is not one that we at this level would need to consider and spend any great detail of time actually trying to identify. The thing about a mass spectrum is that it is a fingerprint, and that every element or every element, every molecule has a unique spectrum that it will create based on its unique fragmentation and mass to charge ratios, etc. Now we've simplified it where we assume that the only mass to the charge is a +1, and that makes our life a lot easier. But a lot more will happen in your mass spectrometer that we do not need to focus on at this level, which is why you will find that some of these peaks, we're not going to try to identify them. So further, when we look at some branch chain alkanes, we see that some fragmentation, as I mentioned before, would result in either a secondary or tertiary carbocation if it is possible for them to be formed. We find a lot of the times that when we have branch chain alkanes, that the molecular ion may be very, very weak or absent altogether, because we are going to produce so many of the more stable carbocations that the molecular ion then simply, not that it will not be formed, but its relative abundance is going to be a lot less than if you were to just have a straight chain alkane or an alcohol or something like that. So again, these things just give you an idea of what is possible. It's not absolute, it's just things that you have to be able to recognize or be aware of. We have some other typical fragments. For example, when we have alcohols, or alcohols will tend to lose fragments or to form fragments by the loss of an OH or 17. We have carboxylic acids that will always produce a peak at 45. Now again, this is a relative abundance at 45 because that carboxylate functional group will get broken off and will fragment in such a way as to have a master charge at 45. Benzene containing structures will often have a master charge at 77, which is going to be the result of the fragment at C6H5, where that benzene ring would have broken off and caused a fragment. We have our halogenoalkanes that will have a molecular ion peak that differs by the mass of the halogen, whether that's chlorine or whether that's bromine. We'll see those in some other examples. Esters will tend to fragment on both sides of the ester bond. So if you are aware that you've been given an ester, you will find that your fragments are such that each piece is going to be put together. On that note, when we look at our characteristic fragmentation, we see that this here gives us an idea in general of what master charge ratios produce what type of groups of atoms or functional groups. So for example, in most cases when we see a master charge of 15, it is because a CH3 has been lost from the molecule. That would usually indicate that you have an alkane and there's some kind of methyl group that has been lost. We saw that the carboxylic acid will give you a master charge at 45 owing to the COOH group. We see also that C2H5 will also tend to fragment and form master charge ratios at 29, and so on and so forth. Now, the bottom half of this are not structures that we are likely to see at our syllabus, but this is just to give you an idea of what then starts to become familiar and what you can now start to look at when you are fragmenting, so that when we start to create our molecular structures, you get an idea of how things will break. So one of the things that we also consider when we look at our mass spectrum, and the reason that it is so good for determining structure, is because we are essentially putting a puzzle together. So when we fragment, we are breaking the molecule up. And if you imagine it as a puzzle, and you've ever built a puzzle, you know that there are different pieces that will fit just right to another piece that will connect to another piece that will connect to another piece to create the biggest picture, and you then get to see the whole. When we fragment, we do the same thing. We break the molecule up into different pieces, and when we identify the pieces based on the mass to charge ratio, we are then able to put those pieces back together and then see the entire picture of the molecule. So in this case, we're given 1-bromopropane, and as a halogenoalkane, bromine, it will have an M+1, which we see at 123, but it will also have an M+2 peak, which is the 122 and 124. So the M+2 peak is the 124 because bromine has isotopes that differ by 2 atomic mass units. It will be a 79 and an 81. If we focus our attention on the molecular ion 122, we see that with the loss of bromine 79, we will create a fragment that has a mass of 43. In this particular spectrum, we see that that fragment is actually our base peak because it is the fragment that has the highest relative abundance. So when we represent our fragments, note how that is represented. The structure is drawn such that the carbon, where the bromine was lost, now has a positive charge. So the fragment is CH3, CH2, CH2, because that last carbon is where the bromine was lost. Again, when we look at the other peaks, we may see some significant peaks, but for the sake of our examples right now, it may not be worth our time to go into more detail about what they are. If we look at this particular example, this again is another halogenoalkane, and we have chlorine 35 and chlorine 37. If we look at our molecular ion cluster on the right-hand side, we see that there's a 78 peak, very small 79, there's an 80, and then there's an 81. So the 78 and the 80 again are the result of chlorine having a 35 and a 37. And we see the structure there with your chlorine 35, 37. If you are asked such a question, you must identify which isotope is giving you which fragment, just as they've done here. They didn't simply just draw the chlorine, they identified that it's the chlorine 35 or the chlorine 37. Now, when we look at the chlorine 35 molecular ion at 78, if we lose a fragment of CH3, we find that there's a mass to charge ratio of 63. That CH3 is most likely due to the loss of that methyl group on the left or on the right. So what we would then have as the structure of that particular fragment will be CH3, CCl, H with a plus on that carbon. If we look to the other side of the spectrum, we may see a small peak at 15. So there'll be a CH3 peak, and then there'll be a CH3CClH peak, and those two pieces will connect to each other to add up to 78. When we look at our base peak is formed again through the loss of the halogen. And again, remember when we fragment our halogenoalkanes, they tend to form stable fragments through the loss of the through the loss of the halogen. So our base peak here has a mass to charge ratio of 43, and that is as a result of losing the chlorine 35. Note again how the molecule has been drawn with the CH3, the carbon with the plus sign where the chlorine was lost, the hydrogen, and then the CH3. Here we have our structure that will have a benzene ring. And when we look at our molecular ion cluster, we see the mass of 108 being the mass of this structure, this compound. And we have an M+1 peak at 109. When we fragment, the most obvious fragment that is there is our fragment at 79. We also have one at 77. So if we consider the fragment at 77 characteristic of our benzene rings, we see that that is most likely owing to that C6H5 fragment. We will also have a C7H7 fragment that would have been formed through the loss of the OH. Remember we said that when our alcohols fragment, it usually will form a fragment that will be less 17, which is that OH. So that C7H7 is going to be the result of that OH being lost from our structure. Excuse me. Here are just some examples of the relative abundances of some of the elements that we may see. Our molecular ions or M+1 contributors. The one that our syllabus will most likely ask us to look at is going to be your carbon and carbon 12, carbon 13 for your, not most likely. The one that our syllabus asks us to look at for M+1 contributor is our carbon 13 isotope. So if you are asked, why do you get an M+1 peak? It is owing to the presence of the carbon 13 isotope in the molecule. However, your M+2, pay attention to the fact that it can be your chlorine 35, chlorine 37, or bromine 79 and bromine 81 if the molecule that you've been given is a halogenoalkane. So let's look at this example here. And the question has asked us to identify the peaks. So they've given us a low resolution mass spectrum of 2-methylbutan 2-ol showing peaks at a mass to charge value of 73, 71, 59 and 56. The molecular ion peak is absent. Propose a structural formula for each of the given peaks. They've given you the actual structure here, and because they've given you the structure, you are then asked to just come up with possible fragments. What is most likely going to be the piece that has broken off at a master charge as given? They've also said that the molecular ion peak is absent. This is also telling you that this could be a branched chain structure, and we know that it is 2-methyl-butan-2-ol. And because it is a branched chain structure, we will not likely see any peak at the far right because the relative abundance of the base peak is so high in comparison. So if you have a look at what I've done here, there are some examples of the structure. So I've drawn the entire structure out, 2-methyl-butan-2-ol. In each of these, on this molecule, you'll see different squiggles, different colors, and different types. There are 4 possible places that I can consider where my fragmentation will occur, where pieces will break off and create a different structure that will have a mass. So the first thing you should do is draw your structure. Get in mind where things can break, where bonds can break, where things can happen. I know that based on the total mass of my compound, my molecular ion, if I had one, would be at a master charge of 88. Now you can start to play with some math here and determine, okay, if I have a master charge of 88, what mass do I need to lose to then give me a 73, 71, 59, and 56? And you can approach it from that direction in terms of 88 minus what will give me 73. 88 minus what will give me 71, so that you go back to, is it going to be a CH3? Is it going to be an OH? Is it going to be a C2H5? What is it going to be? That is one possible way. I prefer to go the other way, and this is one of the ways that you can approach as well, by simply looking at the molecule and not necessarily doing the math. So if I look at that red squiggle at the top, that red squiggle is formed by the breaking of the bond where I lose the OH, which will have a master charge of 17. Losing my OH results in me then having a master charge of 71. And that would be where my carbon now has a positive charge. So this is now the positive fragment, the positive fragment where the carbon is going to be positively charged. If I fragment with my other zigzag where I lose a 15, I see that there are 2 places that I can lose my 15. Actually, let's have a look at the fragmentation through the purple squiggle first, and then we'll go to the next slide. If I fragment with my purple squiggle, that breaks my molecule almost down the middle. And I have a fragment at 29, and I have a fragment at 59. They've asked me for my fragment at 59. And this is going to be my answer here, whereby that molecule has broken down the middle, and my fragment at 59 has my 2 methyl groups, a carbon, and my hydroxyl group attached. They haven't asked me for my 29, but then because we can put the 2 pieces together, I know that these 2 things will connect. If I lose my master charge of 15, there's more than one potential place that I can lose my methyl group, that's CH3. I can lose that CH3 from the carbon to which the hydroxyl is attached, or I can lose that methyl group from the carbon on the far end, which is my N-chain methyl group, right? So there are 2 possible ways. Now, because we are also going to consider which is most likely to be the molecule that is formed, or the fragment that is formed. When I lose my CH3 to form my 73, I have to take into consideration which of these two is going to be my most stable fragment. So when I lose the methyl CH3 from the carbon to which the oxygen is attached, I form a more stable structure because there are two other carbons attached to that carbon than if I lose the methyl from the carbon on the end. So between these two, I would err on the side of the first one as the most likely fragment for 73 instead of the one down at the bottom. Now, I believe that there was an error in this question, so we've not been able to find what 56 is. I may have to get back to you on that. Nevertheless, this here is an example of a past paper and some ways by which fragmentation can occur, and you can, I hope, have a better understanding of how you can approach your fragmentation to determine particular fragments when given a question. So our references again, chemguide.co.uk, and we have some past paper questions for you to try, and I'll see you in class.